more, and possibly, evidently, I didn't make that clear enough at the end of the period yesterday. This section was nothing more than, look at the red there, was nothing more than calculating slopes. I mean, that's what you did the whole exercise for the most part, right? Is calculating slopes. We want to be able, if we need to estimate a slope at a point, then we want to calculate slopes. Now, the other way we have of calculating a slope is the old algebra, the tried and true. If we've got a graph, as you know, we sketch that tangent line. So if I've got this, and we talked about that the other day, and I want to get that slope, we do that, right? I mean, so we have two ways, really, of doing slope. I know with my Algebra 1B class, when we're learning about slope, I draw these two. I got that picture right over there. I drew it for Emily. But I've got these two things I put on the board. I say you can either get slope this way, or you can get slope this way, and you got your choice, right? I mean, depending on the problem. That's it. That's it. So that's all that was going on in this homework, was you were either doing this. Now, if you had a graph, you'd probably do the slope triangle, right? If you had an equation or you had a table, you'd probably just pick two really close points. And then you just answer the question, right? So when they said, so everybody get a hat and log in. You should get a document from me here eventually, as soon as that you do. But so when they said on question 10, for example, when they said to do this this function right here, and they asked you to find f prime of 1.5, then basically it said estimate by zooming. What I would do is I would do f of 1.5001 minus f of 1.5, and then over 1.5001 minus 1.5. There you go. And get in the habit of writing this down too, and get in the habit of using your function notation, right? That's what we've been emphasizing. Our last quiz was about, was function notation. So for your y's, let's use that f notation. That's your y's. And so then on your calculator, now this would be worth talking about. We've talked about it already, but your calculator, so like Emily, you asked, do I trace, okay? Do I need to zoom? Well, it said zoom numerically. I told you yesterday, you could physically zoom, but you don't really need to spend a lot of time zooming in. If I want to zoom in at 1.5, that's right in here somewhere. If I want to get that actual point, I can trace. It's not, this is never going to be an issue where you really have to do this on the quiz. If I hit enter again, it gives me that. If I want to zoom in, okay, I want to zoom in at 1.5, and I want to keep zooming in until that looks straight. If they would say, hey, zoom in until that's a straight line, and then give me the window where that looks straight. Okay, well, there's my window. X min max would be that. Y min max would be that. I'd write that down, right? And I would do that. But did it ever ask you for a window in any of the problems? Did one? Which one? 14A. Find a viewing window perfect. Find a viewing window centered at 3 and where the graph appears to be linear. So there you go. So you zoom in, zoom in, zoom in, zoom in. The graph looks linear. Write down your viewing window. So you would say, okay, so my X window was from here to here, and my Y window was from here to here, and you just get that from the X minimums, right? So don't overcomplicate this, guys, with what they're asking you to do. But to actually do the slope, all you need is, there's one point, and then if you want to trace and get another point, that's fine. If I want to do 1.5001, if I want to do that, I can trace what just happened. Oh, it's rounding. See, I'll be honest, I rarely trace to get points on the screen. I'm just going to do it on my calculator side. Let's just do it over here, right? So, and remember now, this is really an important thing. Let me say this one more time. I'm not sure many of you caught this the last time we talked about this, but if I've got a graph here and I've got this thing stored in F1, how can I find F1? How can I find F1 of 1.5 on my calculator screen? F1 parentheses 1.5 and hit enter. And there it is, right? So that's a quick way to plug something into a function. is put that function in your graph screen, or you could right here, I think I showed you this, maybe if I haven't, let me show you right now. I can type out define. I know we did that with that program thing we did, but I could just define f1 of x, or it wouldn't even have to be f1. It's f1 on the calculator screen, but if I want to just call this f of x, let's just define f of x equals, where's my equals, x squared. And just do it right there. And you can actually type out the word define, or you can go under menu to actions to there, but you can just type out the word define. Okay, define f of x to be x squared. And so now, if I type f parentheses 1.5, right, there it is. And then, so now I can type the whole thing. So I can actually grab myself a fraction here. Whoops, it's not a fraction. Grab myself a fraction right here, and I'm going to type, what the heck is that? Type in f parentheses 1.5001, right arrow, minus f parentheses 1.5, go down, 1.5001, minus 1.5. And just type it in there, right there. Do I have to put the x squared?
Why did you define x squared?
Because that was question 10. Question 10, the function was f of x was x squared, right?
Oh, yeah.
Right? Those first problems, the function was x squared. So I just defined f of x to be x squared. So now every time I call the f function, it's going to plug into x squared. What does f of 2 mean? F of 2 means plug a 2 into the f function, right? Well, I just told the calculator what the f function is. If I want a new function, I'll do define f of x to be something else. Or I could use g of x or h of x or whatever you want. Emily of x, you could actually do that. You can call functions more than just one letter, right? Okay, so I just defined f of x to be x squared, and I just plug it. But you didn't have to do that, right? I mean, don't make it, if that's confusing to you, then just do this. Just do this, just do that. Minus 1 point, just plug it in yourself. You know, just do that, right? You can just do that too if you want it, right? That's the top, and then you got to divide by the bottom, right? It's just a regular calculator, but I'm just showing you that there are some other things you can do with it, right? Where you can give these function names and you can plug in these values, but you got to be able to do this, right? We got to be able to type in and get some different things. Okay, so I wanted to mention 25. So on 25, we got e to the x. Okay, so any question about that? What about the table on 27? Okay, how do you fill in that table? You use the graph, right? It gives you the graph. So you've got, let me see if I've got, I hope I have this, I may not. Okay, so doesn't look like I do. I thought I might have this. No. Okay, so anyway, it gives you a picture of that graph. So when it wants you to fill in f prime and -1, like Skylar and I were just talking about, you just go over to -1, you draw your tangent line, you do your rise over run, right? That's it. I mean, we just have two ways of doing slope. It's one of those two. And so I apologize if I didn't make that clear enough. I thought when I went over this that we had talked about that, you know, that's what I said. Here's what you're going to be doing in section 1.5. You're going to be picking two really close points. You're going to be doing the slope calculation. And then, of course, we had done some tangent line ones already with rise over run. So that's how we can estimate the slope on a curve. Okay, now, a couple of really important questions here of on the homework. I want to talk about 25. Okay, so let's go to e to the x. All right, and so you guys got hats on. Let's get somebody to be my presenter here, and let's have Jesse. You're the one. I'm going to have you be the presenter. All right? Okay, so go on your graph screen and pull up e to the x, okay, because this is number 25. So yeah, let's delete that out of there. Let's pull up e to the x. Max, on your screen, on your calculator screen, I would like you on your F1 to pull up the cosine graph, if you would, because we're going to, or no, the sine graph. Pull up the sine graph. You got it up? Okay, perfect. Okay, so now, on 25, we're supposed to zoom in to estimate the slope at 0.5. Okay, we're not going to manually zoom in, but just trace at 0.5. Just trace for me at 0.5. Okay? All right. Now, there's the point that he just traced at, right? Okay, now, hit Scratchpad, go over to the home screen, okay? And let's do a slope calculation. So I want you to define, and everybody guys can do this with us or just watch it. If you can't keep up, it might be better to just watch, to be honest with you. But just define f of x to be e to the x. So let's define f of x to be e to the x. Okay? And I like doing this on the home screen because it just saves me. And oh, by the way, when you do E, you don't do the character E down on the keyboard. Everybody, right? Understand that? It's by the LN key, right? You don't use the regular E down there. It's a special E. You see its boldface kind of looks a different font. Okay, so make sure you get the right E. Okay, so we're going to define f of x to be e to the x. So now we can use that in our slope calculation. Okay, so now let's do f of, let's do a fraction. Let's get a fraction first. Just go back to the left, hit a parenthesis in front of that F. Arrow back. You don't have to delete it, but arrow. There you go. Put a left parenthesis there. Okay, and then, so this will be the top of our slope. We're going to do a slope calculation at 0.5. So let's go F parentheses. So let's go 0.50001. Okay, 3 zeros. And then minus f of 0.5, right? So that's our y. So we pick two really close points to 0.5. Okay, then go down to the bottom. Let's divide. Let's do divide now. Okay, and then on the parenthesis, and then on the bottom, well, what would it be if you subtract those? Whoa. Now, it's okay, now let's think about this. Would you put f there?
Oh, no.
What are we putting on the bottom? We're just putting the x's, right? And so on the bottom, the top, we're doing f. We're subtracting our y's, right? And it's just going to be go ahead and do that. You can subtract them. It's just going to be 0.0001, right? I mean, so we could just put that there, but that's fine. So this is our slope calculation. Memorize this. You guys got to know slope, right? We got to know slope. We got to understand that that's slope, okay? We got to look at it. Okay, look at that slope. Does that number look familiar? Hit your scratchpad key again. Is that a coincidence? Notice that it says then in part B, is this consistent with the assertion made in example 6 that f prime of x equals f of x? We didn't talk about that yesterday, but holy mackerel, you're kidding me. I don't know if you guys truly appreciate that. One of the things you guys asked me the other day was that what's the big deal about E, right? What's the big deal about E? There it is. That's example 6 right there. There's the e to the x graph. That is absolutely, this is the only graph where this ever happens except, I guess, y equals 0, where the slope at every single point on the e to the x graph, the slope is exactly the same as the y value at that point. It's amazing. Now, y equals 0, of course, every point there has a slope of zeros, but that's what we would call a trivial example. Okay? So right here, where the y value is 1, has a slope of 1. It's the only one of the exponential functions where that happens. Okay? It's the only one where that happens. That alone makes e to the x a pretty special situation.
So is its derivative graph exactly the same?
That's right. Its derivative graph would land right on top of itself. The derivative of e to the x is e to the x. It's its own derivative. Its y values are its slopes. It's an amazing thing.
I got 0.6. I got another one. I was supposed to get 3. I got 33.
It looks to me like your bottom is wrong. Your button, arrow up here. Arrow, no, right there, grab that. You didn't type it in right, hit enter. Okay, and go to the bottom. Okay, now type, what are you typing in there? How many zeros? How many zeros are there gonna be? Look up above. No, look up above, look on top. How many zeros? 3, okay, and then 1. Oh, it's actually, wait, let's go back to what you had. Did we do that? How many zeros are gonna be? I take it back. Since we got a decimal there, I said that wrong. How many zeros are gonna be under here when you subtract this? Do it real quick, Jesse. 1.50001 minus 1.5. There's gonna be 4 zeros because you're gonna get a 0 where the 5 was at. Because this is a decimal place. So you gotta put 4 zeros in. So there you go. Jesse had the right idea after all. Go ahead and type it like that and then you'll be safe, right? Then you'll be safe. Then you won't do the bonehead thing I just did where I subtracted them. Okay? So, oh wait, I'm back to, is that you, Jesse, that's up there? That's me. There we go. Okay? So you should get that. Okay? All right. So that's really cool. Okay, now let's go to number 30. Okay, so Jesse put square root of x up there. Let's go to your graph again, and now let's do square root of x. Okay? Get that out of there. Okay, Max, you're going to be up here in a second, so get ready to roll. All right. Define, oh, you've already got it as F1, right? So it's F1. So we wouldn't have had to define, on Jesse's, we wouldn't have had to define f of x as e to the x because he already had it in F1. So we could have just typed F1 every time there instead of F, okay? But hit enter. Okay, there's square root of x. Okay, 2 quick questions on 30. Why is f prime of 0 undefined? There's the tangent line right there. How come? Because this is a sideways parabola. This is a sideways parabola, so this would be the peak of the parabola. Its tangent line is vertical. There's no slope, right? Did I tell you guys this the other day about a sharp point? I don't know if I told you guys this. What's the slope right there at that sharp point? You'd be tempted to say 0, but it's not right. It's undefined. Here's why. Remember we were talking about that car, if you were going 3 mile an hour, 3 mile an hour, and then all of a sudden you had to switch to negative 3 mile an hour instantly, you couldn't really do that. The derivative is undefined at that point. Okay, so there's 2 places that we're going to say the derivative is undefined. At a sharp point, and then here at a vertical tangent, like this. If you have a vertical tangent, of course, there is no slope there. It's undefined. Okay, so the slope's undefined, and then it says, why is f prime of -1 undefined? There's no point on f, right? You can't have a tangent to a point if there is no point. So you can't have slopes at places that aren't there, right? So that's obviously undefined. But you can have points where there is no slope. If you have a vertical tangent line, or here's another case where you have a vertical tangent line, the cube root graph. It kind of comes up and goes like this, and right here at this point, vertical. So we would say the slope is undefined. Okay? All right. So now let's go to 38. Okay. Thank you for doing that. Oops. Okay, and Max is up. Okay, now this is really cool too. Okay, so what you were supposed to do in 38, a lot of you did not have this done. It did take a little bit of time, and that maybe was where you ran into trouble. But we're supposed to estimate the slope at a couple of places. Okay, so we're supposed to estimate the slope at 0. Okay, well, what would you do? The slope at 0, well, you would pick a couple really close points. So Max, let's go to your home screen. I haven't made you the presenter yet. Let's go to your home screen, okay, and go to your calculator screen. I'm sorry, not your home screen, your calculator screen, okay, and it's already F1, so we don't even have to define it. You can if you want to, it doesn't matter. It's already in F1, right? So let's go to 0, so let's pick 2 really close points. So let's do F1 of 0.000, let's do about 3 zeros, it'll be fine. 1, and then minus F1 of 0. So we're doing the slope at 0, okay? So that's the y's. Now you don't have parentheses around that top, so that's gonna be a problem. Yeah, you need them around the top, otherwise it's gonna divide before it subtracts. There you go, you got it. Just put in the right, get it. You got it. Yeah, just put in the right parentheses there, gave you your left parentheses. Okay, and then 0.0001 on the bottom. And, yeah, okay, good. Okay, and then what? What do we get? So what do you guess the slope is right there? Okay, go back to your graph screen. So that kind of makes sense that would be about a 1. Okay, write these down now. Keep track of these. Write these down at number 38. Okay, so he's got it. Okay, Max, you can't write it down. You got to keep going. Okay, now we're going to go to pi 6. Okay, so now let's do F1, left parenthesis, and then let's do F1. And then let's just do pi divided by 6. Just do pi divided by 6. There you go. And then plus, let's go inside the pi 6. Okay, we need to go a little bit to the right. So let's go plus 0.0001. Okay, we need to go a little bit to the right. There you go. And then minus f of pi 6, right? F1 of pi 6. Okay, see what we're doing here? We're gonna get a y value. We're gonna get a point really close to pi 6, and then we're gonna divide by what? No. Well, yeah, but isn't it just gonna be 0.0001? Right? It's gonna be this, subtract that, right? It's gonna be 0.001, right? Is our run. Very short little run. About 0.866. Does that number sound familiar at all? 0.866? Okay. Doesn't sound familiar at all? Do square root of 3 divided by 2. Square root of 3 divided by 2.
Yeah, that's what I did.
You did what?
I just used to get the circle.
Hit control enter. Control enter. Or there you go, that do it too. That's interesting. What do you mean you use the unit circle on that column?
Well, like, because can I use the...
We're doing the slope though.
Yeah, but can I use, like...
The rise over run.
Yeah.
The rise over run on the unit
Use
circle.
Get a triangle and use the rise over run.
Okay, but isn't that tangent? Isn't that opposite over adjacent? Right, if you do a unit circle, draw a triangle. So where are we at? We're at pi 6. If I do the unit circle at pi 6, right, it'd be 1/2 here. It'd be root 3 of 2 here, and it'd be 1 here, right?
Yeah.
At pi 6. If I do rise over run, that'd be 1/2 over root 3 over 2, which would actually be root 3 over 3. Right? If I simplify that, because it'd be 2 over root 3 if I invert and multiply, so I get 1 over root 3, which would be this.
Yeah.
That's tangent at pi 6, right? Which, by the way, tangent is slope on that because it is rise over run, but that's something different, right? And so that wouldn't be square root of 3, right? Yeah, so it wouldn't be that. So that's a thought, though. That's a thought. Okay. Now, so what are we finding? Let's back up. What did we just find there? Go to your graph screen. So what we're saying is the slope here was 1. Then we went to pi 6, which is what? 3 divided by 6 is about 0.5, so we're about right here. And we said the slope's a little less than 1, 0.86. Does that make sense? Aren't the slopes getting less here? They are getting less, right? They are getting less. So that makes sense. Now what's going to be the slope at pi halves? 0. Okay, so let me do this for you. We're going to stop because this is going to take a little bit more. But if we kept doing this, now I want to make sure you understand what he was doing there. We're just doing slope calculation, right? We were just taking pi 6 on the sine graph. We were doing the slope, okay? So what we were getting, and by the way, we know sine of pi 6 is 1/2, right? But what we just got for the slope of sine was square root of 3 over 2, wasn't it? We just saw it was 0.866, wasn't it? So what we're saying is right here the slope is 1. Let me plot these slopes. I'm just going to plot. Remember, because the derivative, the y value of the slopes, right? So I'm going to plot these slopes. Okay, so I got a slope of 1. And then here at pi 6, what do we get? About 0.86 something. Now we know sine of pi 6. Sine of pi 6, we know that's about 0.5. So 0.88 something's got to be about right there. 0.866 is above that a little bit. Now right here at pi halves, what are we going to get for our slope? 0. Okay? What do you suppose the slope is right here? Don't you suppose it's -1? Wouldn't it be the same slope as it was back here? Okay, the slope's going to be -1 right here, right? And then, what do you suppose the slope is right in here somewhere? Was it going to be about like that? It's going to probably go here a little bit. What do you suppose the slope is on this part of the graph? Right here, the slope was 0.866. What do you suppose it is there? -0.866. What's the slope right here at pi, or 3 pi halves? Back to 0, right? What's the slope right here, do you guess? 1 again? What if you plotted those points? Are you kidding me? This is where you're supposed to go. 1, 2, 3. Are you kidding me? The slopes on the sine curve are the cosine values? Yeah, they are. They are. Unbelievable. Unbelievable. I mean, I get that this one is 1. That makes sense. This one is 0. I get that. But this one right here at pi 6, where we have a y value of 1/2, its slope is actually square root of 3 over 2, which is the cosine value. It is. And here's how we say that. We say that if f of x is equal to sine x, then f prime of x is equal to cosine x. You just learned your first couple of derivative rules today, right? Obviously, the easiest one is this one right here. If f of x is equal to e to the x, and what's f prime of x? E to the x, right? Do you see how if we could have some slope equations, wouldn't that be way better than doing slope calculations all the time? Wouldn't that be way better? If we had a slope equation, if we wanted to know the slope at 1, we could just plug in a 1, and we just plug in a 2, just plug in a 3. Well, there's 2 of them right there. So wouldn't it be great if we had a slope equation for x squared, for example, right? Instead of just trying to find the slope at 1.5 or at 1 or at 2 and doing slope calculations, pick 2 really close points. Wouldn't it be great if we had an equation for the slopes? And then we could just plug numbers in and we could get it. Well, that would be great. And stay tuned to chapter 2 and we're going to get some. Okay? But we've just got a couple right here. We just got a couple right here by just plotting some points. That is amazing. Amazing. Been teaching this for 20 years and it never ceases to amaze. All right. So, let's move on. Section 1.6. So section 1.5 is just, okay, section 1.4 is, okay, derivative, what it is, slope of the tangent line, instantaneous rate of change, all that stuff. And now section 1.5 is just like, well, we might want to calculate this sometime. We might want to calculate some of these slopes. Problem is we need 2 points. We're doing the slope at 1 point, so what do? We pick 2 really close points. Or maybe we do a tangent line and estimate the rise over run. But we might want to be able to do these slopes. All right, so now today what we're going to be talking about is this whole idea of increasing and decreasing and how f connects to f prime. So get your Chromebooks out. Get your Chromebooks out. We're going to try this. I don't know how much time this is going to take, but it's probably worthwhile, so we can do it. Okay? Get your Chromebooks out and let's go to, I've never done this before, so we're going to see. Okay? So here you go. Here's the website to go to. Have you ever done anything? I know you've probably graphed on Desmos before. Have you done one of these before? Activity kind of thing on this? Desmos? Okay? So go to this website here. So our focus the next couple days is going to be what connection does f and f prime have? Now, clearly f prime gives a slope. Okay, everybody get that? Okay, the code's up here in this corner. Student.desmos.com. Student.desmos.com. Okay, and the code's up here in this corner. Okay, Max is in. Now, as people are getting in, don't get started yet, but as people are getting in here, okay, so if f prime is the slope, well, clearly that tells us something about f then, because when the slope is positive, what do you know? What's going on? the F graph. Now, one of the things I'm going to hound you guys about is using pronouns like it. Okay? It's increasing. Don't say that. Right? F is increasing, right? Because if F prime is positive, that means F is increasing. Right? If you say to me, there's power right there. Back in the back, whatever. If F prime is positive, then F is increasing. But F prime could be increasing, and then that's going to mean something else for F. So really, when you're talking about it's increasing, don't say it's increasing, let's say F's increasing. Right? Now, if I specifically say to you what's happening with F, and you say it's increasing, okay, then, I mean, I'm not going to yell at you, but whatever. Okay, so who's not in? Everybody's in. Everybody's in. Okay. All right. Why does it say just 7? Oh, Skylar, are you on? There you go. Okay. Everybody's in. All right. I want you to run through this here real quick and just answer these questions. Okay? Go through here, and this is just about increasing and decreasing, and let's just make sure we're getting all on the same page as far as increasing and decreasing. And I'm going to read your answers here. And I don't care how you give the intervals, whatever notation you want to use is fine. You just want to describe it in words, or you want to use brackets, or, whatever. Here is an F prime graph, right? Right? Let's just look at that right there. Now, are those values always positive right there? Look at that graph. Are those values always positive? Yes. When I say, is that graph positive? But we got to understand the language here now. When I say, if this graph, is this graph positive, I'm talking about its y values, right? They are all positive. They're all above the x-axis, right? Are those values increasing? No. Here they're decreasing. Here they're increasing, right? So a graph can be positive, but not increasing. Those are two different words. So we got to be really careful. Okay, so what we've learned on this screen then is that the graphs, when the F prime is positive, F is increasing. When F prime is negative, F is decreasing. And when F prime is 0, was like at a peak, right? It's flat. Okay, now, everybody go to screen 6. Okay, so doesn't that, why can't I, oh, here we go. Here's screen 6, right? Everybody's looking on this. So let's look at it. It says the orange graph is the F prime, right? So look what happens. When this graph is red, the increasing, what do you notice about the orange graph? It's above the x-axis, right? It's positive. When the F graph is blue or decreasing, what do you notice about the orange? It's below the x-axis. It's negative. When this graph, the F graph, goes back up, increasing, the orange graph is above the x-axis again, positive. And then when the blue graph goes down, when F is decreasing, look at the orange graph below the x-axis. See that connection? Okay? Now, I didn't say anything about when the orange graph was going up and down, right? I didn't care about that. I only cared about when F prime was positive or negative. That told me when the F graph was going up or going down. Now, there is some other stuff going on there, like what about when the orange graph is going down? What's happening with the F graph? I don't want to get into that right now. Maybe you already can see it. But there is some stuff there, but let's don't throw too much in there. Okay? When the F prime graph is going down, something's happening on F. When the F prime's going up, something's happening on F, but it's a different thing. And so we're going to, one of the hard parts of the next couple of days is keeping all this straight. But let's just focus on increasing, decreasing. When F is going up or down, F prime is either positive or negative. Okay, and let's go to, okay, is everybody on 8? No. I got to take you there. All right, so which one of these is F and which one is F prime? Purple? It is purple. The purple is F, and the orange is F prime. Thought the purple was F? Well, let's look at it. When the purple graph is going down, what's F prime? What should F prime be? Negative, below the x-axis. It is. And then this one, when this graph is going up, the F prime, the orange, should be positive. It seems to be. But now Jesse says switch that around. What if the orange was the F graph? Isn't this going up the whole time? And this one's always positive. Could they be derivatives of each other? Well, they're not. But could it be possible that this could be F and this could potentially be F prime and the other way around?
If the orange was the F, would that be like a point missing at 0?
Say that again now.
Wouldn't 0, if the orange graph was F, wouldn't 0 be undefined?
No,
Slope?
because right here, that's just a 0 slope right here.
No, on the orange graph.
Say that again. So
If the orange graph was F,
F.
would 0 be undefined?
Uh-uh.
Slope? Is that vertical line?
No, it's not vertical.
Well, I'm saying, would we draw a tangent line?
Right here, it'd be that right there. That'd
It
be,
wouldn't go vertical like the example before.
no, I had that example where it came up like this. If you were driving a car on this, think of the headlights. When you got right here, it would be right here. Yeah, that's your tangent line, which looks like it might be about 1, which is that Y value right there. That's kind of the trick on this one. Now we're going to do some of this hopefully later today. I don't know how much time we got, but we might try one of these where we do look at 2 graphs, and one is F and one is F prime, and or we have a bunch of graphs, and we want to match up the F's with the F primes, right? And looking exactly at that thing. This one is a kind of a special case where you could make an argument that the purple is F and this one's F prime, and vice versa. They both have, there's really not enough information for sure to tell, but it looks like they could be. Now, this this would have to be, as it turns out, this would have to be, if the orange was gonna be F, okay, this looks kind of like an x cubed, and then this was an x squared, that would work. But if this one was gonna be the F prime, if the purple was gonna be F, this would have to be like an x to the fourth. Which it could be, because an x to the fourth could look like that. And then it's possible that you would get that, okay? So, it all depends. What we don't know is how this is curving. Remember when we did those graphs the other day and we said, well, this one could just be a straight line, right? It wouldn't have to curve like this, right? This one was F. This could actually be a straight line and still be it, right? Negative, then positive. So it would all depend on how much this is curving, and we can't really tell. That's why this was kind of a challenge. Okay, so let's end that. We'll get out of that, and that's what I wanted you to look at. But the main idea of that was this idea of increasing and decreasing and so forth. Okay. Back to our books here. Let me, or back to, let's get rid of this. All right, so this is a thing that I've always shown for along those same lines, but it doesn't really matter here because you guys, I don't really need this anymore, but this is one of the things I sent you yesterday, okay? It was called the derivative grapher, okay? But the bottom line is you got F here, you got F prime, and the same thing is true. When this graph is increasing, right, when the red graph is increasing this whole time, the blue graph is positive, just like we were talking about. And then you get to this point here, and then it goes to negative. The slopes are negative, right? And then you get down to here, still negative, still going down, and then all of a sudden here you get zero slope, and now back to positive. So that's the first and most important thing I want you to understand. Okay, now into your notes. So if we're going to talk about this here a little bit, so in your book on page 55, 56, talks about increasing, decreasing, all that stuff. Now, we do want to make one thing just kind of a little bit of a technicality, but we want to make this kind of clear. If I say the graph is increasing, okay, then its y values are continuing, getting bigger and bigger, or smaller and smaller would mean decreasing. If a graph never changes, like that orange graph we just saw, we call that monotonic. Monotonic. Mono meaning one. Think monotonic means one direction. It just goes one direction, which means it's always increasing or it's always decreasing. Okay, always increasing or always decreasing is monotonic. Okay, all right. So if a graph is always increasing, its derivative would always be positive, right? We would assume. Now, there is one little technicality. Think of the x cubed graph. The x cubed graph is always increasing, but it does have this flat spot right here. Okay? So when we say if f prime is positive, means f is increasing. We would all agree with that, right? That's what we've been talking about. If f prime is positive, then f is increasing. But it doesn't work the other way around necessarily. If f is increasing, does that mean f prime is always positive? Well, here's a great example. Right here, now again, my picture's not great here, Max, but the x cubed graph just has this flat spot right there. Okay, my picture doesn't really look like it. But right here, it flattens just at zero where it has a horizontal. So is the slope always positive on this graph? No. So one way you can say if f prime is greater than zero, if f prime is positive, then f's always increasing. True statement. But if you're going to say it the other way around, you'd have to say if f is increasing, then f prime is greater than or equal to zero. Does that make sense? Okay, so it's a little bit of a technicality, not anything to really worry about, but just understand, you don't want to say, well, this graph isn't always increasing because right there the slope's not positive, it's zero. Well, it can do that. It can just level off and keep going and still be increasing. Okay, still be increasing. As long as the slope never goes negative. Okay, a little bit of a technicality. So on page 55, there's a whole bunch of terms that we already talked about in an earlier section. Local max, local min, stationary point, that kind of stuff. I want to write down a couple of those terms right now for you to put in your notes. These are very important. The term stationary point, okay, of f. A stationary point of F is the x value where f prime of x equals 0. Okay? A stationary point is where the x value where f prime is equal to 0. Now there could be three different possibilities. It could be that, it could be that, or it could be this one we talked about here. It could be that. This is a local max, a local min, or a flat spot. Some books call that a terrace point, okay, whatever. I'm just going to call it a flat spot. Okay, those are stationary points. We're going to use that term a lot. We're going to use that term a lot. Okay? The second thing I want you to write down is critical point of F. And that is the x value where f prime of x equals 0 or f prime of x is undefined. So that's like a larger set, right? So critical points would include stationary points, and then it would also be where f prime is undefined. So that could be at one of these three we just said. It could be at a stationary point, right? Those would be your stationary points, but it could also be at remember we talked about that being where the slope is undefined right there, right? We talked about that. We also talked about a vertical tangent. So like if you had a graph like this, where it actually had a vertical tangent, that kind of thing. Okay, those would be your classic examples of places where f prime is undefined. Okay, no matter what, critical points and stationary points are points of interest to us, right? Because if you look at it, it's where the graph is flat, which could be a max or a min. You could have a peak, like a sharp point, that could be a peak. It's where the graph changes. In this case, the graph changes from increasing to decreasing. So something interesting is going on at those points. So those are points we're going to care a lot about. So critical points and stationary points. In the early stages, we'll talk a lot about stationary points. We'll ignore these sharp points at weird places where something crazy is happening. But then later on, we'll bring those in more. So in the early stages, we worry more about nice graphs that are smooth and that curve and that don't have those sharp points, okay? So we don't get into those a whole lot. All right, let's see. Local versus, we talked about local max and global max the other day, so I'm gonna skip over that. We're talking about what f prime tells us about f, stationary and critical points. All right, so let's do this next. Okay, I sent you that document that I sent you at the beginning of class called the first derivative test. Okay, go ahead and pull that up. So you go to your home screen. Right, go to your home screen. You can go to My Documents. Oh, yeah, I'm sorry, my screen doesn't look like yours. I already pulled mine up. I already got it. But go to Home Screen, My Documents. It's called First Derivative Test. Okay? All right. So you're going to follow along through this worksheet here. Okay? And so if you look at the worksheet, it says, oh, pull mine up here. I thought I had it. Hold on a second. we go. All right. So you're gonna work your way through this. So, okay, report these definitions. A function f has a critical point if the value c is in the domain of the function, right? And either f prime is 0 or f prime is undefined. So that's what we talked about, a critical point. A function has a local max if when x is near c, that is, f of c is greater than x in some interval. So in other words, it's just saying, so it's the largest point in that interval. So we already talked about local max, local min. So you're ready to move on to here, okay? So you've got this table, okay? So it says grab the white point on the x-axis and move it to see the slope of the tangent line change as you move along the graph. Complete the table below. So you're given this, hang on, am I on the right page of that? Did it say go to 1.2? Each page of problem 1 in the document has a graph of a function with a single critical point. Okay, oh yeah, on the side, 1.2, 1.3. Okay, so 1.2, so right here at 3, there is a critical point, right? So right here, I'll just do this first line with you, okay, and maybe you're ahead. So it's at x equal, the critical point is x equals 3. It said reason why it's a critical point. So what would you say? Well, you'd say, okay, x equals 3, and then why is it a critical point? Because the slope is 0. So I would just say f prime of 3 equals 0. You just write that right in there.
How do you move that?
Okay, the best way to move that is these right here. These arrows, probably. You can grab the white dot. It's easier for me on the computer than it probably is for you to grab the white dot. So if you just want to go up with your trackpad and hit these up and down arrows, and it'll move it. Okay? So the up arrow moves it right, and the down arrow moves it left because you're changing the x value. Okay? So now, it's just your basic parabola. So back to your worksheet so you understand what they're wanting. Okay, what's the location of the local max, local min, or neither? So we already said this is x equals 3, and it's a critical point because f prime of 3 equals 0. Okay, location of local max, local min, or neither. So in other words, this critical point, is it, what they're saying is it a local max, local min, or neither? What is it? It's a local min. So they're not asking you for the location. They're saying, okay, is this location a local max, local min, or neither? Okay, what are the intervals where the slope is positive? 3 to infinity. What's the intervals where the slope is negative? Negative infinity to 3. There you go. Now you go on to the next page and find that critical point. And then talk about it. Local max, local min, neither, whatever. And you're going to keep filling in these tables as you go through these different documents. And you're going to be learning something about, okay, you're going to be learning about local maxes and local mins. That's the point of this worksheet. You're going to be learning something about local max and local mins. How you can tell that you have a local max and a local min based on the slope. Based on the increasing and the decreasing kind of things. Okay? Never include, when we're doing increasing, decreasing intervals and stuff, never include. Let's don't include them. Yeah, those inputs, because that's where it's changing, increasing to decreasing. So just as a rule of thumb, just never include what we're giving those. Okay? All right, go ahead and work on that for a little while here. Oh, you need a partner. Yeah, you better work with it. Let's see, I could. Or I could just put it up here. Just tell me when I need to go to the next page. Oh, it's frozen. So you got that stuff already, right? Yeah. Okay. There you go. calculator battery's about to blow up, like those Samsung phones or something. Look out. All right, so, you can go ahead and keep working on that, we just have a couple minutes left. So, the next line on your assignment is 1.6, day 1. Okay, and so 1.6 is several days here, so it's 1.6, day 1, there's a handful of book assignments, and then finish this worksheet, okay? So finish this worksheet, and then, the book problems. It says first derivative test activity, that's what you're doing right there, the worksheet, okay?
What is day 1?
On your assignment sheet. So it says so your homework for tomorrow is 1.6, day 1. See that line? So it's those problems. And then the first derivative test activities, that worksheet. Okay?
Can I see my,
And guess which one we'll do tomorrow? Day 2. There you go.
can I see my quiz? Did you hand those back?
I did.